Hey, welcome to the next channel. So a year ago I shot a video on process versus threads, and this is not a video meant for students or beginners. This is for advanced system software architects, where I discussed about the implication of spreading the load across multiple process versus in terms of multiple threads in a single process. I have also discussed in case if you keep more and more accumulating more and more threads in a single process, the question is, in case if any of the threads instances gets crashed, it is going to kill the entire process, and this is an bad situation in a data center device or something like a network carrier grade equipment. So you need to also take these things into consideration. So you need to choose an option between how you better utilize the CPU in terms of doing a load share of your batch processing or whatever it is, because this is a sort of scenario where you have many workers and doing some kind of a similar job, taking some input and then dumping some output externally. So this is what it is. So when you architect something, this is what I have discussed, and what I have done is I have also done an project to benchmark the CPU. It is quite a simple project. I hope some of you guys have already seen. It's called as Truebench. So the Truebench is essentially very simple. I have also mentioned what are the objectives of Truebench and where exactly the applications of Truebench make sense. So Truebench, what I'm doing is I'm measuring a single core performance of a system, like a single dimensional performance of a system. So this way what I can do is, because the source of Truebench I kept it very simple, it just does a combination of mem sets and mem copies, and there are people who argued this is not a way to benchmark the CPU and other stuff. Essentially I'm not even benchmarking the CPU. Please understand, I am benchmarking the overall system. If you have more cache in a CPU, these things will happen more or less in the CPU cache itself. Otherwise, if you have less amount of CPU cache, you need a bottleneck between CPU to RAM bus channel. So if the channel is faster, you are going to get a better score. If the channel is slower, you are going to better score. So end of the day, it depends on the RAM hardware. It is DDR2, DDR3 or DDR4 or some kind of mobile RAM chip, or it also depends on the processor architecture. It is Intel, or it is in Intel it is desktop versus server platform, or it is AMD, or it is not x86, something like ARM or MIPS architecture. So this is the objective. So these things you can do if you keep the benchmarking software as simple as possible. So essentially what happens is, if I start my benchmarking software, it is going to latch on to a single core of a processor, and then it is just going to do all this iteration in that core itself till it dies out. It is going to latch on to that single core. So assume you have quad core processor with hyper threading. You have 8 cores in the system. So if you run Truebench, it is just going to latch on to a single core, and it is going to evaluate the performance of the same. So this is the way. What you can do is you can compute truly what is the true potential of a specific core of that processor series. So one can expect always, you should understand, than any high-end server processors or even multi CPU architecture, always desktops are going to better perform. The reason is to do gaming and high-end desktop operations. It can be even something like editing this video or tasks like that. So all these tasks requires exceptionally good quality of core level performance, not essentially having multiple cores. So sometimes it is very important, and even if you compile the kernel, you need both core level computational power as well as having as much cores as possible. So this way it's going to compute as fast as possible. And also, if you couple with SSD or something like that, of course the IO is also going to be optimized. So this is what essentially makes a good system. So why I am discussing about these things is, what I have done is, for this demonstration I have taken the Truebench code So before I discuss the Truebench code, what I can do is I can do a very quick short demo. So this is the Truebench x86 64 bit version. So you can just run it as a normal user. You don't need to be an admin to run the same. So if you run, before that, let me open this system monitor. So you can see here not any specific CPU is showing 100%, and it is just this is the optimal usage of my computer with all these applications which are opened. So what we can do is we can run this Truebench, and now you can monitor here. As you can see here, only one core out of this 12 cores, because this is a 6 core processor. With the 6 cores you have with hyper-threading, it is 12 cores. So I'm sorry. So with 12 cores, it shows one specific CPU core is latched. The Truebench is latched on that specific CPU core, and it is using the same core. So this is what is an intentional behavior. Please understand, I don't care how many cores you have. I'm only decided to. My objective is to only test the performance of a single core. So this is where what we can do is we can test the performance of a process in a system with multiple threads, with multi-threading and without multi-threading, because this is not something you just read in the books and you get conceptually. This is something, a physical stuff happening in the physical hardware. So this you have to really notice. So you can see here, once the Truebench is over, its performance is again the load is again dropped down, so it is again at the optimal load. So you can see it is clearly like it just latches onto a single core and it does the same. So what I can do is I can just show a quick glance of my source code before I hop on to the one which I have introduced multiple threads in the same. So you can see this is the source code. The reason I have shared also the source code is in case if you have a different hardware platform or something, you can compile the source code with whatever instructions, or otherwise 99% I suggest you don't. In case you want to submit your Truebench benchmarks, test only in your physical system. Don't test in any VM, test in a physical system, and the system or operating system like Linux installed on a physical system. And second thing is you also don't open much any apps, just bare minimum apps, and then run Truebench, and you will get the result. If you are not satisfied or convinced, you can try a couple of times. Or if you have a laptop, sometimes you can consider about dusting it, so that it gives you the better performance. The reason is, if there is a lot of dust accumulated in your cooling fans, it is going to degrade the performance, because the processor often tends to get hotter very soon. So this is subtle effect, but it gets amplified as your processor gets fully loaded. So that's what it is. So it's quite important. You can dust it out once with a vacuum cleaner or something, and then you can do the Truebench with a couple of tests or a couple of samples, and then if you take those samples, you can submit the same. So this is out of this process and threads agenda what I'm discussing in this episode. So this is just I'm casually telling. In case if you're curious, you can send the same, and I can include your Truebench score of your specific hardware in my website as well. So you can see here the source code is very simple. I'm doing a dummy load, nothing fancy. It is having this mem copies and mem sets, and then I'm capturing a dummy result. The reason I need to capture the dummy result and I need to print on the screen over here somewhere is the reason is, as you can see here, the real output shows somewhat like this. So the reason is, if you don't do anything, there can be some situation where GCC can optimize this code, and it can completely do away with that dummy load API. So it knows that, okay, this API is not essentially doing anything. So although you are running the API in the main API, you are not doing anything. So why GCC should even include the object code or assembly code in the same after it is compiled. So this is the reason it is quite important to have the dummy output and or a dummy result, and then just dump on the screen, so that GCC doesn't do any sort of optimization. And this is something which is also quite important for us to catch that really whatever it is expected out of that benchmarking platform. So let's hop on to our modified code, whatever I have modified. So you can see here, by the way, before going, you can see here it is just a straightforward load, dummy load API, and it doesn't have any threads or any such fancy stuff. It's just in the main API, it is I'm calling the same, and before calling I'm taking a timestamp of get time of the day, and again I'm doing get time of the day, and then I'm doing a diff and I'm displaying on the screen. So as simple as that is. So this is something been widely argued in some discussion forums, saying that this is not a true way to benchmark and all. I don't really care. So this is something I'm intentionally doing. If they don't understand, let them just not understand. That's all it is. I'm intentionally doing this. I don't want to see what each module inside a CPU to test, like ALU. Okay, what are the components of ALU and other registers in a CPU and all its capability. It's not the objective. The objective is to test the overall system performance in terms of its computational power to an extent, and especially this data transfers, because you should understand it's not adding A plus B takes time in a processor. It is actually this storing this data and then retrieving the data to the registers all the way from RAM to the CPU cache, and CPU cache to the registers, and do the computational stuff on this data and then storing it back to this system. This is where it takes a lot of time. Okay, so this is what it is. So this is the reason I don't care what is the overall performance of those MIPS and other stuff in a traditional sense, because it doesn't make any difference. The main thing is you have to check this way. So you can see this we can take as a reference to load our system. So the context why I am taking this code in this video is to load the system just like what you have seen. So what I have done is I have just took the same code. I didn't add the time, I didn't change any of those file headers. I just kept the same. So you can see here in the dummy load I have done a minor change. I have brought in all this global variables inside, because I need to keep this as a self-sustained API so that it can be called multiple instances in multiple threads, as you can see here. So here I am creating two threads, and pthread, and you can see here I'm registering the same API multiple times. So this way both threads is going to run the same API multiple times. And please understand, if you are a beginner, if you are really new to threads, just skip this video. It is quite difficult to understand. This is not an introduction of threads. I'm assuming that you know already some theory about the same, the theory about the process, and you know the theory of threads, and you know the major differences between process and threads, and then you have also worked on some projects, and then suddenly you are watching this video. This is for people who are in the industry, and also some kind of system architects who are trying to find some answers and trying to find some evidence. So this video is meant for them. If you are a beginner, you are watching, you can just watch it as a time pass, and if it is not entering somewhere in your mind, you can just feel free, just watch it, don't think much. If you are unable to understand, just it's fine. Okay, just it is have fun. Okay, so this is what essentially is happening. So what I have done is I have compiled the same. You can see here I have compiled the same. So what we can do is we can run this Truebench binary, and then we can check how far this differs versus that other one which is pre-compiled long ago. Please understand that is not I have compiled now. I compiled that source code very long back and then I have published those binaries in the website as well. So you can go here and you can download whichever it corresponds to your hardware, and you can test the same. So you can go down and you can run the same. So now what is happening is there are two threads running simultaneously, that benchmarking stuff, dummy load or whatever API, and then it is running the same. So if you run this with multiple threads, please note, you can see here there are totally two CPU cores which are latched in. You should understand this is not going to decide, anytime you run a process, it is not going to decide which core it is going to latch in again next time. It is not starting from core 1 and all these things. You can of course change this affinity inside the kernel parameters and stuff like that. We take an ideal system, a generic system, and then if you run, this is what is the nature of things which happens inside a system. You can see here now it has hooked to the core 5 and CPU core 8, what I can do is I can cancel this, and right after I cancel this, you can see here there's a drop in the system load. All the cores are again in its normal state. So once again, if I run, it is going to suddenly latch on to some other cores. You can see here in this instance it is latched on to CPU core 1 and core 5. So like this it happens each time you cancel and again you run, it is going to latch on to any of those 12 random cores. Okay, so if you can't still believe, what I can do is I can save this as Truebench 2, and what we can do is essentially we can remove this entire thread part. Let's take the entire multi-threading part and we retain only the dummy load stuff. So this time we call it as a normal API. So let me remove all this arguments and other stuff. Okay, so with that what we can do is we can run the same. As you can see, I have removed all the threads. It's just a very simple API and we are calling the API inside the main. So let me compile this Truebench 2 gcc -o Truebench 2 truebench2.c. Yeah, I think I need to give, okay, since there is no thread, you don't need to give lp thread and other stuff. Okay, it's compiled. What we can do is we can run the same Truebench 2. So now if you go here, you can see once again it has latched onto a single CPU, but not like before. It is latching onto 2 CPUs with threads enabled. So you can see here, this is what is the behavior happens. So the takeaway lesson for a system architect is, if you have a user space process and assume you have multi-core CPU, don't assume it is just going to span across all the cores. And if you are upgrading your system from dual core to a quad core to a 6-core CPU, or the upcoming the latest AMD's Ryzen or Threadripper processors, don't assume it is just going to span across all the CPU cores. It is not going to happen. What multiple CPU cores gives you is it is going to give you an allowance to run as much as applications as possible simultaneously, but each of such application is going to be limited, or instance it is going to be limited with respect to the core level performance of that CPU. So this is what it is. So you can see here, this time it is latched on to CPU core ID8 and it is showing 100% it is loaded. So this is what it is. So you can see here with threads, if you have time or if I want, I can even do one more thing is we can even create one more pthread and we can demonstrate. But anyway, this is what is going to happen with my one more pthread. What is going to happen is it is going to now overload 3 CPU cores and it is going to show 100% performance. So that's all guys for this episode. I hope you learned something today. As I said, this is not for beginners or students. If you're done away with learning the basics of operating systems and the overall process architecture and various subsystems in a Linux kernel or Linux system, then this will make sense as the way you are in your career. So that is what it is. So if you are still a student, you may not fully understand what are the implications. So that's what it is. So if you guys want to discuss something, you can reach me via email. As I discussed recently, I have removed YouTube comments and other rating mechanism from YouTube. I don't care they do like or don't like. It's just I started to understand YouTube is a nice platform to share videos. Let's not rate these educational videos. And some people, some of my students or some of my clients know that I know astrology. So astrologically my moon sign, it corresponds to Lord Krishna. So I behave more like Rohini. So I like the status of guru. As I do knowledge share, I don't like somebody putting some racist comments and saying this is an Indian saying this is someone saying that. I don't care what caste or creed and all that stuff. I value education, and education should reach everybody. This is what is the reason I started this channel. So I don't want to hear all those bullshit comments and some people saying holding the mic properly, do this, do that. I'm not open to all those things. So that's what it is. That's the reason I have removed the comments. Since it is just a couple of videos before I have done, I'm still discussing about it in a couple of these videos. So that's about it. So if you guys want to reach me, send an email across. In case if you have any questions, send an email across so that you can get clarified. So thank you once again for watching this video. Have a nice day. Bye bye.